Let's continue. Let me open the table of content first. Okay, we are on chapter 18, still on chapter 18, patching introduction, and on homework simulation here. Let me open that. Okay, we are in this section, homework simulation, basically trying to understand how translation from virtual to physical address works with the patching technique and linear patch table. Okay, we already take a look at question 1, question 2, question 3, and now we are in the question 4, right? Yeah, basically trying some different parameter, and yeah, there is this question: which of these parameter combination are unrealistic and why? I'm assuming this one because the page size is too large. So one process, what is it called? This can cause internal fragmentation, something like that. So inside the page there is too much space that might not be used. So there is something that, and yeah, maybe this one that is unrealistic. Maybe, I mean, yeah, the address space 256 megabyte might also be unrealistic if it is for the stack, but if it is for the heap, might be realistic. Yeah, I'm not sure about the address space here, but the page size might be unrealistic. Okay, now let's try with this parameter. Let me open terminal emulator. Okay, the info here, and then VM patching. Okay, page size 8K, address space 32K, physical space 1 megabyte or maybe byte. The binary representation and set is 2. Okay, yeah, something like this. Virtual address, this one. Wait, let me copy the virtual address first. Okay, let me do some calculation. First thing first, we need to get the virtual page number, right? Okay, and the page size is 8. The page size is 8, maybe something like 8K. I mean, 8K. Okay, this one. Let's use logarithm. Okay, so something like this, the address, the virtual address, right, masking by the complement of the page max, basically the maximum value that can be held within 13 bits or something like that. Yeah, I mean, I can show that, I guess. Oh, what is it? Something like this. See, if I use this one, the actual page size, it will become 14-bit. Something like that. So the complement of that, and we got this one, and write shift to 13 bits. Okay, something like that. Virtual page number 2, right? Wait a minute. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, interesting. Okay, complement is 14, right? Anyway, virtual page number 2, width is invalid in this case. Alright. Okay, 10,097. Okay, what is it? Yeah, let's put that in a variable. Thing like this. Oh, interesting. Okay. Write shift by 13 bits. 1, virtual page number 1. It is invalid again. Alright. 19855. Okay. achieve better than invalid again. Okay. 1983. Really? Okay. Alright. Look like it is in the same page range. Okay. Alright. Yeah, looks like the last one is also in the same page range, in the same page as the previous two. Invalid. Okay, let's check that out. Yeah, invalid. All of this is invalid virtual address. Okay. Now let's try this one. Okay. One maybe byte. 256 maybe byte. Okay. The random set is 3. Oh, there is a lot. Right. Yeah, the address space is also a lot. Okay, that is quite a big number. Virtual address here. Marks to remove the offset marks, and also right. One maybe byte. Okay. Multiple 1024. Okay. Something like that. Can we do this? Oh, wait, no. Remember, it is a negative one, so it should be something like this. Okay. also do this if I want to. Right. Okay, there is that. And max. Alright. Yeah, let me check the exponent of this one. 20, okay. 2 power 20. Alright. So right shift by 20. Okay, 48. Oh, okay. The base number 48. I think this one, right? This is the page frame number 502. And then for the offset, wait a minute. Okay, for the offset it is the page max. Yeah, something like this. The page size -1. And then page mark. Okay. This is the offset. And then base frame address, basically the base address for the page frame before we adding the offset there. Okay. Page frame number, this one, left shift by 20. Okay. This is the base address. And then we add, and then we use the bitwise OR to add the bit from the offset here. Something like that. What is the offset again? Oh, 569933. Okay, it's quite long. Okay, that is the first one. Now into the second one. And max. Okay, right shift 2066, virtual page number 66. Width is invalid. Wait, right, this is invalid. move on. To this one, 47. It is not invalid. Okay. Right. Page frame number 169. And what about the offset? There. I think this one. I don't think that is correct. Page mark. Again. This is the page mark from the page size 1, maybe 5. Okay. And then this is the offset. Let's take a look at the base address from the page frame. Okay, no. 169 left shift 20. Yeah, that's a lot of number. Alright. Page frame address with the offset there. What is the offset again? I think this one, right? Yeah. Okay. And then we cut this as the physical address. Alright. Okay, virtual max, virtual page number max there. Alright. This is the base address for the virtual page, and we need to get the, what is it called, the virtual page number or the index from this base address, something like that. 180. Okay, let me check. 180 is invalid. Okay, it didn't have the physical address yet. That make me curious. Virtual page number 47. Wait. Oh, it is it's not the same. Okay, but wait. Can we like left shift this to 20? I don't think. Oh, right. Okay, that's because the extra 1 bit here. Okay, now let's try this. shift by 20 bits. Virtual page number 219. Let's check that. Okay, this is not invalid. Width is valid. Okay, page frame number 498. What about the offset here? Page marks. This is the offset. Oh, that's quite a lot. Okay, 498. Okay, 98. Left shift 20. Okay, this is the page address for the page frame. Using OR bitwise operation. I think this one. Okay. This is the physical address. Something like that. Let's see if it is correct or not. Okay, the first one is virtual page number 48. Okay, and then this is the physical address 526 955 085. Okay, all right. And then the second one is invalid, right? On virtual page number 66. The third one on virtual page number 47, right? This one with this page address 178.173.563. All right, and then the next one is invalid. Okay, on virtual page number 180, right? And the last one is on virtual page number 219. This one, with the physical address 523030196. Okay, so I guess that is correct. And now let's continue into the question 5. Use the program to try out some other problems. Can you find the limits of where the program doesn't work anymore? For example, what happens if the address space is bigger than the physical memory? If I remember correctly, it will throw an error, I guess. But yeah, we can try that out. Address space size bigger than physical memory. Okay, something like this. This is the address space 512 gigabyte or maybe byte in terms of the binary representation, and the physical address or physical memory is 256 maybe byte. See, physical memory size must be greater than address space size. So yeah, I think we can check this out from the simulation. For the limit where the simulation doesn't work anymore. Oh, there's also the condition to use less than 1 gigabyte. Okay. Interesting. Let me check. Right, must use smaller size. Okay. Yeah, you can take a look at the script, the simulation script about the limit of the simulation. So I guess let's continue into chapter 19, Paging, faster translation, or TLP, or translation TLP, I guess. Let's take a look at that. Translation look aside buffer. Chapter 19. Using paging as the core mechanism to support virtual memory can lead to high performance overhead. Can lead to high performance overhead. I'm assuming this means that it can be slow, maybe something like that. Maybe by chopping the address space into small fixed size unit, that is pages. Paging requires a large amount of mapping information. Paging requires a large amount of mapping information, right? I think that is one of the two problems here. Wait. This one, page table might be too big, right? And also might be too slow, at least from the chapter 18. Wait a minute. Yeah, in this chapter. Okay. Because that mapping information is generally stored in physical memory, paging logically requires an extra memory lookup for each virtual address generated by the program. Paging logically requires an extra memory lookup for each virtual address generated by the program. Generated by the program. Okay. extra memory lookup for each virtual address generated by the program. Going to memory for translation information before every instruction fetch or explicit load or store is prohibitively slow and thus our problem. The crux: how to speed up address translation. How can we speed up address translation and generally avoid the extra memory reference that patching seems to require? How can we speed up address translation and generally avoid the extra memory reference that patching seems to require? What hardware support is required? So we are assuming that we need a hardware support. Okay, what operating system involvement is needed? Alright, when we want to make things fast, the operating system usually needs some help, and help often comes from the operating system old friend, the hardware. Okay, the old friend. Alright, to speed address translation, we are going to add what is called, for historical reason, a translation look-aside buffer, or TLB. To speed up address translation, we are going to add what is called translation look-aside buffer, or TLB. A TLB is part of the chip's memory management unit and is simply a hardware cache of popular virtual to physical address translation. Thus, a better name would be an address translation cache. A TLB, or translation look-aside buffer. Wait, is that? Translation look-aside buffer. TLB, translation look-aside buffer, is a part of the chip's memory management unit, MMU, and is simply a hardware cache of popular virtual to physical address translation. Popular. What is the definition of popular here? Is it the translation that frequently accessed, translation that frequently going, maybe something like that. Thus, a better name would be an address translation cache. Upon each virtual memory reference, the hardware first check the TLB. Upon each virtual memory reference, the hardware first check the TLB, or translation look-aside buffer, to see if the desired translation is held therein. The desired translation. Maybe popular in here means the frequently translate address. maybe frequently translate address. The hardware checks the translation log aside buffer to see if the desired translation is held therein. If so, the translation is performed quickly without having to consult the page table which has all translation. Because of their tremendous performance impact, translation look aside buffer in a real sense make virtual memory possible. Okay. TLP control flow algorithm. Okay, we have this virtual address and also the virtual page marks. Basically, what is it called? Basically masking to highlight the virtual page number bits, the binary digit, by removing other than the virtual page number bits, and then right shift to get the virtual page number. With this expression, we get the base address for the virtual page, and then by doing the right shift, we get the virtual page number or the index for the virtual address where the virtual address resides. Okay, and then TLP lookup. Success. TLP entry is success true. We check if we can access the, what is it called? The entry, I guess. The translation entry, maybe something like that. Okay. Okay, we get the offset here, right? By removing the, what is it called? By removing the virtual page number bits, the binary digit, using the offset marks. And then this one, right? From the page frame number and left shift, we got the base address for the page frame, and then using the bitwise OR operation with the offset bits, we got the physical address. For this translation, for this virtual address translation, and then access memory. Okay. I forgot what is the protection bits. Did I take note? No, not in this one. Maybe in my note here. Let me check. Protection bit indicate the permission of the virtual page address. Oh, is the page could be read from, written to, or execute from. Okay. So it is the permission. If we can access this translation look asset buffer entry, we can access the memory, right? If not, we raise an exception. Okay. Oh, TLP miss. So if, what is it called? If there is no entry in the translation look aside buffer, I assume it is called TLP miss, and we are doing things manually, I guess, checking if the what is it called, checking if the address valid or not. What is PTA in here means? And what is PTPR? Yeah, I need to figure this out. The abbreviation here. Okay. Retry instruction. Okay. TLP basic algorithm. Figure 19.1 shows a rough sketch of how hardware might handle a virtual address translation. Assuming a simple linear page table, that is, the page table is an array, right? Similar to previous chapter 18, linear page table, right? This one, linear page table, and a hardware managed TLP, translation look asset buffer. That is, the hardware handles much of the responsibility of page table access. We will explain more about this below. The algorithm that will follow works like this. Okay, well, I think let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.